Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honours Physics students, and we are going through a course of lectures on optics, and in the section on interference we have gone through the case of thin films, the wedge shaped films. We saw the air wedge, fringes of equal inclination, Hadinger fringes, Newton's rings experiment to determine the wavelength and refractive index. And in the lecture 20, the contents will be as follows: determination of wavelength of sodium light by Newton's rings. Number 2, determination of refractive index of a liquid using Newton's rings, and lastly Hadinger fringes. We saw in the last lecture the experimental setup which will be used to obtain the Newton's rings, and the experimental setup, as I told you, goes as follows. What you have is the base of the microscope, wherein you have got the glass plate. This is the glass plate that you are keeping here. Above the glass plate is the convex lens, and in between the convex lens and the glass plate you have naturally a air film. This air film will not be wedge shaped. In the case of air wedge, which we saw in the earlier lectures, we have a wedge shaped film. You got a glass plate. Above that there is another glass plate, a plain glass plate, because of which you get a wedge shaped film. But here is the place where you have got the lens exactly in contact with the glass plate. Because of that, the air gap is 0 here. The air gap thickness, it keeps on increasing from the center to the rear edge, and similarly from center to the point L here, LP, right. So when you have a bright point here, depending upon the conditions that you will be having, either the constructive interference or destructive interference. What do you mean by constructive and destructive interferences? The 2 rays 1 and 2, which are coming from the point C and similarly from the point D, these 2 rays interfere with each other. Depending upon the condition for constructive interference or destructive interference, you will be getting either a bright point here or the dark point. If you get a bright point with this as the radius, you will be getting all the points corresponding to this radius to be bright. If D is bright, then all the points whose radius corresponds to this point from center to D, you will be getting a circular bright ring. On the other hand, if D becomes dark, then corresponding to the radius, you will be having a dark ring. So, you will be having rings instead of straight lines in the case of air wedge. In the case of air wedge, what you got were, you got bright band, dark band, bright band, dark band. Recall, in Fresnel's bipolar experiment also, you got the bright band, dark band, straight lines. Air wedge also you get straight bands, dark band, bright band and so on. Here you get circular rings, and similarly in Hadinger fringes, which I will be talking about toward the end of this lecture, there again you will be getting circular rings, which will be of course having lesser intensity, but the point is here in the case of Newton's rings, they are called rings, so you got circular rings, okay, the bright and dark rings depending upon the condition for brightness or darkness. And the rings that you have will be looking like this. You see the dark ring here, you got a dark ring and then a bright ring, dark ring and so on. You see the crossfires, right? You got the two crossfires, and our aim is to use this Newton's rings to determine the wavelength of the monochromatic source. You got a monochromatic source. Let us assume this to be a monochromatic source. You have got a sodium vapor lamp, that is a monochromatic source. You know the experiment setup which I showed you just now. You have got a source here, then you got a lens, then a glass plate which is kept at an angle of inclination of 45 degrees. The reflected light will be coming and passing through the Newton's rings setup, and you will be having a telescope here using which the rings can be seen. And when you see the rings, you have the crossfire also. You make the crossfire to coincide with the left of this ring, right? Similarly, the left of this, the same ring. So, the left of this and the right of that, the same ring will give you the diameter. So, the diameter of this ring is obtained by, how do you obtain the diameter of the ring? You make the crossfire to become tangential to the left. Similarly, move the crossfire and make it to become tangential to this edge. Then obviously, the difference in reading, the microscope reading that you have got will give you the diameter of that particular ring. Similarly, if you want to take this ring, for instance, second ring, make the crossfire to coincide along this edge, it becomes tangential to this edge, and move it to the right, make it the crossfire to come here and make it to become tangential with this edge. Then the difference in reading that you are taking when the crossfire is tangential to this edge and similarly tangential to this edge will give you the diameter of that particular ring. So, the diameters of the various dark rings, or you can choose the bright rings. Either way, either you can use the bright or dark rings. So, determine the diameters of the various rings, and from the diameters you have got an expression connecting the diameter of the ring and the radial curvature of the lens and the wavelength of the sodium vapor lamp. So, the procedure that you adopt will be as follows. With the help of the travelling microscope, the diameters of a number of dark rings are measured. You take a look at them, the ring pattern, you go to the extreme left. Say for instance, you start with the 18th ring on the left side. Whenever you are using a travelling microscope, you are not supposed to go back and forth. That means you should have only a unidirectional motion, right? You start from left and go to the right. Don't go from left to right and then back to left and so on. So, you should have only unidirectional motion in order to avoid the error. So, start from the 18th ring on the left, then 18, then 15, then 12, 9, 6, 3, come to the third ring on the left, go to the third ring on the right, then 6th, 9, 12, 15, 18 and so on. So, you start from 18th ring on the left side, go to the 18th ring on the right side. The left side you take the 18th ring, you take the reading, right side you take the reading corresponding to 18th ring. That difference will give you obviously the diameter of the 18th ring. Similarly, you can get the diameter of the 15th, 12th, 9th, 6th, 3, third rings. And so, you get the diameter squares of the various rings, or the diameters can be obtained from that. You can take the diameter square. So, the position of the microscope is adjusted to get the center of neutron strings at the point of intersection of the crosswires. The microscope is moved until one crosswire is tangential to the 16th ring. It may be 18 or 16. So, you go to 16th ring, from 16 you go to 12, from 12 you go to 8, from 8 you go to 4, then from the 4th ring on the left you go to the 4th ring on the right, 4, 8, 12 and 16. So, now you have to tabulate all the readings, and the microscope readings are taken. Then the microscope is moved such that the crosswire of the is tangential to the 12th, 8th and 4th rings, as I told you just now. The readings are noted in each case. Readings corresponding to the same rings are taken on the other side of center. So, if you take the reading for the 12th ring on the left, then 8th, 4th, then you go to the 4th again, 4, 8, 12, 16 on the right side. Then, as I told you, the difference in reading between the 16th on the left and 16th on the right will give you the diameter of the 16th ring. Similarly, the diameter of the 12th, 8th, 4th rings. So, the diameters of the various rings are determined, right. Things can be tabulated, and again the squares can be obtained, ought to be obtained, because the expression that you have to determine lambda will contain the squares, dm square minus dp square. What is dm square? M refers to the order of the ring, the mth ring. It may be the 8th ring or the 12th ring or the 4th ring and so on. P may refer to again 4, 8, 12 and so on. Therefore, what you do is the readings are tabulated as follows. You take start from the 16th ring, take the reading on the left side. So, from 16th you go to the 12th, then 8 and then 4. Then you go to the right side. Then you come to the 4th ring on the right side, the 8th ring on the right side, 12th ring and 16th ring. So, the difference between these two will give you the diameter of the 16th ring, because you take the reading, this is the 16th ring, okay. You have taken the reading for the left side, then you have taken the reading on the right side. So, the difference between these two readings will obviously give you the diameter of the 16th ring, that you have to find. The diameter of the ring D will be A minus B, the left and right, the difference between A and B will give you the diameter of the 16th ring. Then you have the 12th ring here. The reading that you take on the left side, make the crosswire to be tangential on the left side, make the crosswire to be tangential with the 12th ring on the right side. So, the difference between these two readings will give you the diameter of the 12th ring. Then similarly for the 8th ring, then the 4th ring. So, the diameters of the various rings, the 16th ring, 12th ring, 8th ring and 4th ring, all these things are obtained. Then take the squares, d square, then dm square minus dp square. So, you have your m and p. So, you can take you can have m minus p to be equal to 4. So, you have your dm square minus dp square. You take the average value here, okay. The average value of dm square minus dp square is found for an air film. What is n is equal to 1? The refractive index of air is 1, okay. So, the diameters of the pth and the mth rings are given by, the pth ring may be the 16th ring and the mth may be 8th ring or 4th ring. So, your dp square for the pth ring, the dp square, the diameter of the pth ring square will be 4p into r into lambda. Similarly, your dm square will be 4 into m. M is the order of the ring and r into lambda. So, you can now find dm square minus dp square will be 4 multiplied by m minus p into r into lambda. What is capital R? What is R? R is the radius of curvature of the lens. You know, you have got a convex lens. The radius of curvature is nothing but you have a convex lens placed on a plate. So, this forms a portion of the surface of a sphere. You complete it, you get a sphere, right. This forms an arc. This forms an arc. That will become a two-dimensional case. It is circle or it is a part of a sphere. In a 3 dimensions, you are from the point L, you go to the right side, that L forms a part of a sphere. For the sphere, the radius of the sphere is a capital R. That is your radius of curvature of the lens. For the lens surface, the radius of curvature, the center of curvature will be somewhere here. You draw a circle, then the center will be somewhere here. So, this is the radius of curvature, the radius of circle, right? The radius of circle. So, you have to know, or you have to determine the radius of curvature of the lens. From that, you have to determine the lambda. We will have a stop, we will have a break here. Welcome back. I have been telling you the method of determining the wavelength of a monochromatic source using the Newton's rings setup. You have an expression like this, dm square minus dp square to be equal to 4 into m minus p multiplied by r into lambda. So, r is to be determined separately. Only if r is known, lambda can be determined. So, from this expression, what do you get? You have the mathematical expression for lambda. Lambda goes as follows. Lambda will be, you keep lambda on the right side, so that your lambda becomes equal to dm square minus dp square. The whole thing that you have got here will come to the denominator, namely 4 into m minus p into capital R. So, your lambda is given by an expression of this kind, wherein in the numerator you got dm square. What is dm square? That is the diameter of the mth ring. The second one is that the square of the diameter of the pth ring. Mth ring may be the 12th ring and pth ring may be the 4th ring. Okay, you got dm square minus dp square, that divided by 4 into m minus p multiplied by r. As I told you, if r is known, r has to be determined separately. You take a scale and go to a wall and get the image and get the radius of curvature of the lens. So, r should be determined separately. So, if r is known for the lens, the radius of curvature is known, lambda can be determined, because in the tabular column you measured your dm square and dp square. You have taken the average from the rings, you have taken all the readings, you have taken the average. The average is to be substituted the numerator, and the m minus p is known, and r is now known. So, lambda, the wavelength of the monochromatic source, can be determined. So, this is the method by which the wavelength of the monochromatic source can be obtained. Remember, the wavelength of any source, the wavelength will be in the order of angstrom unit, which cannot be measured in any other easy manner. You have to go to some sort of optical experiment like Newton's rings or average, and whatever be the thing. Or I will be talking about various interferometers, especially the Michelson interferometer in the next lecture, and you have to use the Michelson interferometer or Newton's rings or average to determine the wavelength of the monochromatic source. The wavelength of the source will be in angstrom. What is angstrom? It is 10 to the power of minus 8 centimeter. That cannot be measured by other methods. Therefore, the velocity of light using the Michelson interferometer, and similarly the wavelength of light again can be determined using the Michelson interferometer. Interferometer is a big chapter. So, the Newton's experiment can be used to determine the wavelength of a monochromatic source like this. Not only that, the refractive index of a liquid also can be determined using the Newton's ring experiment. As I told you, the radius of curvature or the lower surface of the lens is found by Boy's method. Substituting this value of r, the average value of dm square and dp square with m minus p is equal to 8 in the above, lambda is calculated. So, this I am just explaining how lambda can be determined, because you know the various parameters in the numerator as well as the denominator, lambda can be determined. So, this finishes the first section of today's lecture, and now we move on to the second part, namely determination of the refractive index of a liquid. So, the determination of refractive index of a liquid using again Newton's rings. What do you do now? You have the same experiment set up as we had earlier, excepting the case instead of having air as a medium, you have a liquid. You put a liquid drop here, you few drops of liquid above the glass plate, then place the lens. Thereby, what you get now, you get a air film. You got a liquid film. Instead of air film, you got a liquid film. The liquid may be water. The liquid that you are placing on the glass plate, you got a plain glass plate, you have a liquid here. So, the medium here, instead of air, you will be having a liquid. Now, you may ask the question, what will happen to the Newton's rings? Now, in the case of air, you have Newton's rings. Now, first of all, whether in the case of when you have a liquid drop, whether you will be having rings at all. Now, if you are having rings, what about their diameters, right? I am going to determine the refractive index of the liquid medium. The liquid medium is kept between the lens and the glass plate. Now, what will happen to the rings? Whether you will be getting rings of the same diameter or of bigger diameters or smaller diameters. Now, this is an important question. Now, where do you get your n, the refractive index? The point to be understood is n, that the refractive index will come in the denominator. In the case of a liquid, n will come in the denominator. So, whatever I had earlier so far, this is for air film. For air film, n is equal to 1. Remember, all these expressions that you have got here for dm square, dp square, you have got dp square, right? Dm square. Now, your all these things, your n will come in the denominator. If n comes in the denominator, what do you understand? What about the refractive index of water? Is it 1 or greater than 1? You know, for refractive water or any other medium is a denser medium, right? Glass is 1.5, the denser medium. Water comes in between air and glass. You know very well by other methods, you can determine the refractive index of water, that you would have done it by other methods by now. But whatever be the thing, you have got a denser medium. So, because of the fact that n is coming in the denominator, what happens to the rings? The diameters will be decreasing. Your dp square will be decreasing, because the value that you are getting in the denominator is greater than 1. Instead of 1, n is equal to 1, you got 1.3. So, your the diameters will shrink. If you have got Newton's rings earlier like this, then you got for all the rings are observed in this region. Now, when you put the water medium, that the rings will be getting shrink, the rings would have shrunk. So, the diameters would have decreased. The diameter of the 12th ring in air will be greater than the 12th ring in the case of a liquid, right? Similarly, the diameter of the 16th ring in air will be greater than that of the case of water. So, the entire ring pattern would have shrunk. Now, therefore, that is an important point. So, the diameters would have become smaller now, because n comes in the denominator. So, again, I need not repeat the same thing. The transparent liquid of refractive index n is introduced between the lens L and the glass plate. This is what I told you just now. You have the medium, air is replaced by water. The lens is placed over the glass plate. Whatever the important point is, you have got water, the medium between the lens and the glass plate. The diameters of the pth and the mth dark rings are determined. You know, in every case, you have to determine the diameters of the rings. But the point I want to emphasize is the diameters would have now would have reduced because of the fact that n comes in the denominator. That is an important point. So, the diameters would have reduced now. As in the case of the earlier case, now you will be having your lambda, the wavelength is the same, the lambda will be the same, but only thing is your refractive index will be coming. So, because you know the wavelength, the refractive index can be determined, right. You know the wavelength of the sodium vapor lamp, so the refractive index can be determined. And in the case of your dp, dm, the diameters that we have been talking about, now the n will come in the denominator at a point, that is the important point, right. So, you have the dp square, the expression that you got here, dp square 4p in r into lambda. For air film n is equal to 1, for liquid film n will come in the denominator. Therefore, you have your the difference between this expression that you got for air and the one that you are getting in the case of liquid is for the case of liquid, as I told you, dp square will contain n will come in the denominator. Therefore, again, because you have calculated the wavelength of the sodium vapor lamp, the refractive index can be determined. Now, we will pass on to the last section, namely the Hadinger's fringes. Now, the experiment part I told you regarding the determination of refractive index of the liquid is important, because even if you get 1 or 2 drops, the refractive index can be determined using the Newton's rings experiment. And the same refractive index I will show in the next lecture can be determined by Michelson interferometer. Now, we move on to what are called Hadinger fringes. Now, the fringes that you get now will again be circular, similar to the case of Newton's rings experiments. The only thing is the intensity of the rings that you get here will be slightly lesser, and to improve the intensity you make use of a convex lens. That is the point number 1. The second point is, instead of here also you have a monochromatic source, you got a monochromatic source, but instead of a point source you got a extended source, as I will be showing in the picture, as I will be showing in the figure. You have an extended source. So, the other point is the film thickness will be large. In the Hadinger fringes, the film that you are going to have will be, the thickness of the film will be larger. In thin films, interference fringes are formed due to the path difference 2 mu t cos r between the overlapping rays of light. The change in path difference is obtained by differentiating the above expression. That is the path difference, right. The change in path difference is obtained by differentiating the above expression, that delta lambda, by differentiating you get 2 mu t into delta cos r plus 2 mu into cos r into delta t. When the film is uniform, the constant thickness, the change in path difference is only due to the change in r. Now, t matters. So, you have a film here, right. You got, as I told you, you got an extended source. You got an extended source. Now, this I matters. The I is the angle of inclination. You got a source of light, right. You have the light ray is coming here, getting reflected, and it is made to pass through a lens, and the image is obtained here from A. You get a prime. These two light rays will give rise to A prime. The light getting reflected from the top surface, then getting reflected from the bottom surface, will give rise to the point B prime. Is that right? Now, you got A, B here, A and B giving rise to A prime and B prime. That is that you have on the screen. So, this explains the formation of Hadinger fringes. What do you understand? The number 1, the film thickness will be larger. Number 2, the source will be an extended source. Let me now pass on to the summary of the lecture. The summary goes as follows. Newton's rings experiment is used to determine the wavelength of the sodium vapor lamp or any vapor lamp of monochromatic light. The same experiment can be used to estimate the refractive index of a liquid, and lastly, formation of Hadinger fringes explained. The questions are: number 1, give the expression for determining the wavelength of a monochromatic source using Newton's rings. Question number 2, how do you estimate the refractive index of a liquid using Newton's rings experiment? Question number 3, explain Hadinger fringes. With this, we come to the end of lecture number 20. Thank you.